Okay, so here we're going to take a look at one of our first tracker labs, and it's based off of the lab that we did in class where you all tried to design your own, dropping an object and making measurements in order to try and find the acceleration due to gravity. Now, as you may remember, most of you got pretty terrible results, and with good cause. It's not a good way of going about it. One of the big things that you noticed was human reaction time would have a huge effect on what you measured. Well, that's what we're going to try and cut out with the video that I had you do. Now, I've installed, and apparently there are Java updates available, totally ignore that. I've installed Tracker and got everything hopefully set and ready to go. So what I'm going to do is I'm going to go to File, and I'm going to do Import. Now, if you're doing this at home, you'll need to find where you downloaded the file. I should have put it up on our class webpage where you could access it. It'll be under the Tracker Labs page. Alright, let's see. I set up a new folder here for us. If you're doing this on the computer that I've set up for you in the classroom, then that's actually the computer you're looking at right now. On the desktop, right here, there's a folder called Tracker Labs. We're looking at Lab 2D, and then student data, you can save your information in that folder, student data, but our video is actually right here. So I'm going to, double click on that. And it's going to take a moment while it loads the video in. It's a video that I cut down a little bit. It'll give you an error message of some kind. Basically, it's saying frame 0 is a little wonky, so ignore it. That's okay, we're not relying on it anyway. Here is a cut down version of the video that you had seen in class. Now, I came prepared. I actually went through and I found the frames in question. So I'm going to pause this. I can drag the little slider back over, and I know that I let go of it right at about frame 15. So here's 12, 13, 14, and there's not really much movement with the puck. Here's 15, and then you'll notice in 16 there's a small nudge as it moves. I'm going to rewind to frame 15. You can see it nudge up there. So frame 15 is when I should be dropping it. And then it continues falling until, now it smears out there because the camera's having a hard time tracking it, but it looks like I can rely on it up to about frame 31. Right after that, it looks like it hits the ground. So I'm going to trim my video. That's the video strip, the film strip up here. I'm going to click on that, and I want to begin on frame 15, so I type in 15, and end on frame 31. Now, real quick, I'll point this out. This one says that it's a frame rate of 30 per second, 30 frames per second. In other words, it's standard video. That'll come into play with some of our future tracker labs. All right, after I've done the film strip, I like to go in order. The next one is to teach this thing how long a meter is. Now, I'm going to drag this over to the bottom side of the meter stick, and this one up to the top. Do not forget to change this. By default, it's 100. If you end up with something where it's 100 times bigger than what you expect, it means you probably forgot to update this. That's okay. But you can double click on it and then just type in 1.0, or you can always come up here and actually adjust it here. Now that I've set that, I can click this button again and hide it. It doesn't mean that it's disappeared, or it doesn't mean that it's no longer at work. It just means that it's not blocking your view. Now we're going to create our coordinate axis. I'm going to set my origin right on the bottom of this little checker piece, this little chip that I'm dropping the puck. And what I'm going to do is I'm going to the end. It looks like it mostly falls in the negative y direction, but here's where, as I mentioned before, you can make your axes whatever you want. And just to make certain that we've got it all in one dimension, I'm going to bring this down and drag the other end of it, holding left click, down to the same point on the puck that I've been looking at. That way, if my camera isn't fully level, I now have pretty much all of the motion that's happening along this axis. Great. Now I can hide my axis. We're pretty much done. Well, we've got a little bit left. Then we go to create a point mass. And my computer is thinking, there it is, point mass. There we go. And then you'll notice that I have a white arrow cursor. If I hold down the Shift key, it becomes a square crosshair. And what I'm going to do, we're on frame 15, I'm going to click on the bottom of the puck. And then it goes to frame 16. It made a little point over here. Basically, it's keeping track of all the points I select. And I'm going to manually select the bottom of the puck each time. I'm going to do my best, but honestly, just like everything else that's done by humans, I don't expect it to be perfect. Honestly, even if we were having the computer do it, which I'll show you later, it probably wouldn't be that reliable because as you can see here, it starts to blur out. Now I'm using the mouse wheel. If you have a mouse wheel, you can actually zoom in and out. It's up to you if you want to do that. Go ahead and play around with it since I did accidentally zoom in. Now if I stop here and let go of shift, we can see all the dots I've selected. You can see that they're not all in a straight line because I'm not perfect. And they may not be perfectly spaced either, but they should be a pretty good indicator of what the overall effect is. So here I go, I'm selecting the bottom as best I can each time. And that's actually why I selected the bottom, because as this thing gets smeared out from motion blur, even in the camera, I can still kind of make out where the bottom is. If I had gone for the middle, I'd have a much harder time getting an exact, or even close to exact, location. Now you can see that we have a nice curvy line. For those of you familiar with it, it is concave up, which means the second derivative is positive. In this case, I made my positive x direction downward, so the acceleration due to gravity is actually in my positive x direction, as strange as that may sound. That's how I set up my coordinate system. All right, now that we've got this, I can actually take a quick peek at the velocity in the x direction, the x component here, velocity versus time. Now one of the things that I'll point out real quick, you'll notice that this is kind of a straight line. It's kind of wiggly a little bit, but part of that's because I'm not very good, well, I'm not perfect, I should say, at putting these points where they exactly would fall. But we can see that this is overall probably a pretty straight line, and if we assume it goes through 0, 0, bit of a stretch, and it looks like it's finishing up right at about 5, and then we've got, let's see, a time of about half a second, and 5 meters per second. If I were to find the slope of this line, with it being the velocity versus time graph, then it would actually be about 5 divided by 0.5, which comes up to right at about 10 meters per second squared. That's what we expect. Now the nice thing about Tracker is it can actually calculate up the velocity pretty well. All right, we're going to go back to the position versus time because that's actually what I want us to work with. Oh, down here, there's a table of our data. And what I can do is I can go to the table. It comes up with both the x and the y. I'm going to ignore the y. Why would I do that? Well, if we look at the y position, this is how much it moves in the y direction. Remember, y in this case is left and right because I moved my coordinate axis. It moves by, looks like about 1 millimeter is what this thing is saying. So in other words, it pretty much stays in a straight line in the y direction, so we're going to get nothing out of that. That's okay. So what I want you to do, come down here to the first cell, left click on it, and it'll turn it blue. Then scroll down to the very bottom, hold down shift, and left click on the bottom right. You'll see all of them have turned blue. Now I'm going to copy. You can either use Control C or you can do copy selected cells. Let's go full precision. Why not? And go over to Excel. Now that we're in Excel, you can hit Control V or you can right click and do paste. There we go. We've pasted our data and now we've got all of our data there. Okay, so first thing I'm going to do is this. You do not have to do this part because it's what I used to ask for, but I'm not going to ask for this one, at least this time. Select data, add, and I'm going to call this a position versus time graph, or at least my data is. So my x, my horizontal, is going to be time, and my y, I click these little window shade buttons. That's what I call them. They put it into a window shade mode that lets you select stuff. Then I hit that, and then bingo. I have now recreated exactly the graph that you see right here. Except it's in Excel where I can do all sorts of neat stuff with it. In fact, what I used to have you do, add Trendline. I used to go with a polynomial second order and display equation on chart. And then we would find that this term here, the number multiplied by x squared, is actually 1/2 of our acceleration. Off the top of my head, looks like I got almost 11 meters per second squared. That's okay, I'm going to push this out of the way because that's not what I want you to do this time. I'm going to bring this back up real quick and we're going to explain what you're going to do. Now this is what we talked about the day after you did the lab. We're going to linearize this graph to analyze our data, just like you would on an exam, for instance. First off, we need a relationship. We recorded position, delta x, how far it fell, and the time, how long it took to fall. We're looking to measure the acceleration, so we need a relationship that has all of those things in them. Well, there's the kinematic equation that you see here. Delta x equals v naught times time plus 1/2 at squared. Now we're going to clean it up some by realizing that we dropped the object, so its initial velocity is 0 meters per second, and that means that that middle term actually all goes to 0 and disappears. That leaves us with the following. For our problem, delta x, the displacement, is equal to 1/2 at squared. Now, to make a straight line, we need to have y equals mx. Technically, y equals mx plus b, but the plus b would just move the line around. Y equals mx is what gets you a straight line. Now, I use color codes in class. I'm going to show them here. The blue, our y, is going to be whatever we graph on the vertical axis. The red, our x, is whatever we're going to graph on the horizontal axis. So, if I look back at my equation, delta x equals 1/2 at squared, I could graph delta x on the vertical axis, and I could graph t squared on the horizontal axis, and my slope would be equal to 1/2 a. That's the other part that's in there. We have y equals mx. However, while that would be perfectly fine, and you are welcome to do that, what I'm going to do in this video is I'm going to switch it up a little bit. I'm going to move the 1/2 over, and what I'm going to do is I'm going to graph delta x, my displacement, as my vertical axis, and I'm going to use Excel to do 1/2 t squared. Now, I don't usually do this on the exam stuff because squaring the time and then multiplying it by 1/2, that's extra clicking that I have to do on a calculator. But here, I'm going to be using Excel, so it's pretty much the exact same amount of work either way. So I'm going to generate a graph that the slope is actually what I'm looking for, the acceleration. So I'm going to generate delta x, my displacement, on the vertical axis, and 1/2 t squared is what I'm going to put on the horizontal axis, and I should end up with something that is pretty much a straight line, and that slope, the slope of that line, should be a measurement of my acceleration. Let's find out. Going back over here. So what I really need is I need 1/2 t squared. So I'm going to mark that. I'm going to do equals. Equals is how you tell Excel to do math. Well, first thing I'm going to do is the 1/2, so I'm going to do 0.5 times, that's the little asterisk, t times t squared. And now we grab the little box down there and drag it down just like we did in class, and it calculates all of this for me, which is my favorite thing ever, because I'm lazy. Insert. Let's go over to our charts. I'm going to insert another chart, except this one is the one that we're actually after. So I insert a chart, and I go down to Select Data. Now, hopefully it didn't actually populate any data. If it did, select it, hit Delete, and then click over in the empty space. I'm going to click Add, and I'm going to call this series Position versus 1/2 time squared. It's a big title, but it describes what we're looking for. My series x values, my horizontal, is going to be 1/2 t squared, and my y values are going to be my position, the x column. Let's see what we get. Do we get a straight line? Indeed we do. All right, now I want you to left-click on one of the data points itself, and then right-click and go down to Add Trendline. Great. Now, there are a lot of options over here, but this one appears to be a pretty good fit with a linear relationship, so we're going to leave it on linear. You could also go with polynomial. You could go, yeah, let's stick with linear. Last thing that I want, and this is important, somewhere in here, you may have to press a different tab, but it'll say Display Equation on Chart. That's what I want you to bring in here, and drag it up here where it can be seen easily, but we have y, which is my position, equals mx, my slope, and my x is 1/2 t squared. Well, my slope, according to this, is 9.798, so about 9.80, which, as we said, if I graph my displacement versus 1/2 t squared, the slope should be equal to my acceleration. This is me making a measurement of the acceleration due to gravity. All right, we're almost done. Let's clean this up a little bit. I'm going to left click on my vertical axis. and right click, and let's go down to Format Axis. Now on this one it hides it over here, sometimes you see stuff back up here. And so let's see, number is one of the things I'm going to go to. Scientific notation, let's decimal places, let's call it 1 decimal place. Alright, I don't want scientific notation, let's do just number. That looks good. That makes that look a little bit better. And then we also want, let's see, labels next to axis. I should have a place where I can actually add axis options. Give me just a moment. I need to remember, oh, chart tools. Okay, I'll deal with that in just a moment. Let's fix the other one here. Format axis. Let's see, number. Scientific, no thank you. Let's go number and then to 2 decimal places. That looks good. All right. Okay, so sorry about that. It was right in front of me. So what you can do is click on the graph and then go to Chart Tools, Design, so not Format, but Design. Then we're going to do Add Chart Elements. They put them in different places all the time. It's a little weird. Anyway, primary horizontal axis. So I'm going to click that, and you'll notice there's a little box here. You can come down here and you can say, honestly, what we really need, since in the title we say that it's position versus 1/2 times squared, all we really need are the units. So I'm going to do seconds, squared. Okay, and then come back over here, add a vertical one. Position is in meters. So I apologize about that. Probably should have come a little bit more prepared. So this is the chart I'm looking for. Now, one thing that you might do is in the title of it, you might put something like Sanchez. So my name for me, not for you all. Go ahead and put your name in there if you would. And then after you do that, you can just left click on this, you can drag it around, do whatever so that we can still see this. I very much want to see your measurement for the acceleration. And honestly, you all should want to see that. The whole point of this lab is to give you all an idea of where that 9.8 comes from. Now, if you get a different number, don't freak out about it. Part of it comes down to, while we are reducing the human reaction time, we are still clicking on something that's kind of hard to click on. We're going to see other ways that we can fix that up. Now, the last thing that you can do is, first off, if you're on this computer, simply go to File, Save As, and then we can go to Desktop, anytime now, Tracker Labs, Lab 2D, Student Data, and then put in something that keeps track of the fact that it is yours. I cannot stress this enough. I've been through too many engineering presentations that everybody names their files my presentation, and it takes 6 hours for people to figure out which one is theirs and which one isn't. You'll notice that I give files very strange names, but I always know exactly what that file is. I like to start with the year because it helps keep things sorted. That being said, I could do ES Sanchez Lab 002D. That would be perfect. So as long as I've got it there, that's fine. Or if you're at home, you can always take this, Control C, so we could copy it. You could go into PowerPoint, for instance, and then you can paste it. It'll take a moment. My computer's a little slow. We can drag this a bit bigger, and then you could always print this off. It's whatever you want to do. So you could give me a hard copy. You could always email the file to me. It's whatever you want to do as long as I get a hold of it. If you do it on this computer that I've got set up in the classroom, that's perfectly fine, but I want you to save it in the correct folder. So student data here. In fact, you can see there's my document, and then send me an email letting me know exactly where it's at. Okay. The important thing about it is we've now taken measurements based off of our video, we've turned them into data, and we've taken that data and put it in to do a complete analysis on it, including linearizing our graph, and you can see that we end up with a pretty good measurement for what the acceleration due to gravity actually is.